Hope you can hear me well. Can you guys hear me?
Yes, sir.
All right, good. So, as I said, this is a beautiful photograph and also a very meaningful photograph. What it means to me, what it looks to me is the sun fostering the life on Earth, provides all the energy required for the plants and animals, right? Beautiful. Um, so, we are actually discussing about the sun. We started the discussion last week. If you want to put it into point form, enumerated like basic facts, energy generation inside the sun, and how when that energy comes out of the sun, and finally to the earth to foster life here, right? And then the internal structure, sunspots, differential rotation, magnetic fields, and finally space weather. But we don't want to make it too technical. This is humanities module. We want to learn, of course, right? But without being trapped in too many technical details, right? But having said that, you just can't have information here and there without any rationale, without any meaning, without any physical description. So therefore, we have to go into that level to understand the physics, right? Because we're all good in physics so that you can enjoy it. I think we went through this list. I don't want you to remember any of these things, not any of these things, but most of the things, right? There are certain things I really recommend you remember, right? What's that? Say, for example, the angular diameter of the sun is 32 arc minutes. So that is about half a degree, right? You can actually close the entire sun with your thumb. If you stretch your arm and align with the sun, you can see you can close it completely, right, with the thumb. Because usually for average human being, when you fully stretch your arm and thumb up, it's about half a degree. And also composition is easy to remember. 75%, three quarters is hydrogen, and the rest is helium. Okay, like that. And the surface temperature 5,800. I think you guys remember these things. I think from a long time ago, right? About sun's temperature on the surface 5,800. It's yellowish, right? So it's good to remember the numbers. Sometimes when you study, you don't really want to remember numbers. We also, as professors, we don't dictate you remember anything, right? But the theorems, the laws of physics and stuff like that, the technique, the methods. But it's always good if you can remember certain things, right? And the mean density is roughly about 50% more of water, right? It's better. It's more than water, because even though it's a gas, it's very highly compressed, right? Body, like that. So this is the black body radiation curve of the sun. If you can see the sun through different wavelengths, different colors, using filters, you can see sun is glowing brighter in some areas, some colors, some wavelengths, and but it's not glowing that bright in other wavelengths or colors, right? We usually say colors for various wavelengths, even though we can't see them all, right? So I think you can understand that. The yellow area is roughly the peak of the sun. Here it is not very clear. It looks like green, right? But it's actually yellowish. Then we know around that about violet, blue, and on the other side, red, orange, whether they are brighter or how bright with respect to the intensity of the peak color, which is yellow. Then you can plot the curve, right? Then figure out, okay, what is the temperature of the sun. A lot of things can be deduced from the curve. So what drives the sun? It's basically the nuclear synthesis, right? Nuclear reactions that's happening deep in the core of the sun. Some of the numbers here, I think it's very handy if you remember them. Sun's total energy output is 10 to the 26. I think it's easy to remember, 1026 watts. So for hydrogen to fuse into helium, you need to have the temperature about 10 million degrees of Kelvin, 10 to the 7, right? So you reach that temperature at the very core of the sun. So that's why it gets the nuclear fusion going. Now, this is basically advanced level physics, but I think it's good to know this fusion reaction is basically conversion of mass into energy. Okay, the famous Einstein equation, E equals mc squared. One side is mass, the other side is energy, right? If you can convert energy into mass, how much you're gonna get? You can simply calculate in this using this equation. So let me show some details, right? Don't take it too technical, but on the surface, you can logically understand what's happening there. So what you see here on the left, far left, is two hydrogen nuclei, right? Two protons, hydrogen one. They collide each other, right? They glue together, and they form a body, right? It's not a single body, but multi-object compound body. Hydrogen and a proton and a neutron, right? So let's call it hydrogen 2. 2 means the mass. Now it's 2 units, okay? And when it happens, it emits a neutrino, a massless particle, zero momentum. You can say zero energy also, right? A small particle. And also it produces E plus positron. This is the identical to electron, but opposite charge. Okay, you have heard of that. This positron is not very stable. Stable means live long. Okay, but these guys, they're not stable. They have very, very short life. Immediately, what happens is that in a blink of an eye, this positron combines with an electron, E negative charge electron. Okay, because this positron and electron, this is a pair of antimatter, right? So the antiparticle of electron is positron, and the antiparticle of positron is electron. So the moment you have a particle and its antiparticle, it doesn't take time, right? Immediately they combine, then annihilate. Annihilate means they disappear. They combine and disappear, and the total mass is converted into energy, and you get two gamma rays. This gamma rays means energy. Okay, so you can immediately see what happens to this mass in the electrons. Okay, there's a small mass that disappears. There's no mass anymore, but there's energy converted to energy. So that's only the first part of the chain reaction. So now what you have as a result of the first part is a H2 nucleus, right? H2 nucleus. It's a hydrogen, it's a proton and a neutron. And then it gets collided with another proton, okay, in the second stage, and then produces two proton and one neutron. This is H3. Let's call it H3, helium-3 nucleus. Okay, so it's basically three masses, atomic masses, and it also gives out another gamma ray. So small amount of energy, which means every time you see this one, you can figure out that the mass of the output, okay, is smaller than the mass of the input, right? If you look at just two protons and one neutron, okay, combined together. Here also you can see very much the same thing, but this is little lighter than this. Okay, the difference of the energy is converted into gamma. Then in the third stage, you get helium-3, two helium-3 nuclei, right, combining together to form helium-4. This is basically molecule, helium molecule, right? In fact, this is only the nucleus of the molecule, because to form that you need to have hydrogen electrons around it. And when you write down nuclear reactions, you do not usually talk about atoms, but only nucleus. You know that, no? Because it cannot maintain the electron cloud around the nucleus. And this third phase of the nuclear fusion reaction gives out two hydrogen nuclei, H1. Okay. So, and in this stage, there's no energy output. Energy is given out in the first two stages. Now, if you combine all three stages and look at what goes in and what comes out, okay, it's basically four hydrogen nuclei. Hydrogen nuclei means four protons, right? Going into the process through all three stages, okay? Actually, you have six going in, but you get two out. 6 in, 2 out means actually you get 4 in, okay? So 4 hydrogens is the total input, right, to the process, and the output is helium nucleus plus neutrino and some gamma rays, which means energy. Okay. So this is what's happening inside the sun in one single nuclear reaction, a chain reaction. We can explain that quite easily. Now, in every second, if you look at every second, just 1 second, okay, 600 million tons of hydrogen. So that's very massive, right? 600 million tons of hydrogen converts into helium to power the sun. Enormous amount of power. So the calculation you saw the numbers 10 to the 26 watts. That much of joules per second, okay, coming out of the sun. At this rate, the sun can continue the hydrogen burning for more than 6 billion years. Irrespective of the rate of burning 600 million tons of hydrogen every second, though because it's so big, it can still go, right, continue burning at that rate for another million years, billion years, 6 billion to be precise. Now, in fact, there are a lot of things we do not know about the sun. Okay, so what I'm explaining you is very simple description about the very complicated object. Okay, based on the evidence, the scientists have modeled the sun, and they have figured out that the internal structure of the sun can be explained as three regions, right? The innermost is the core that you can see here as gray color, relatively small. And then around that, you have the radiative zone, which is the biggest part of the sun. And outermost is the convective zone. So just three. Again, I think for you guys, it's easy to remember. How many different sections in the sun, internal structure, layers or whatever, is three, okay? Energy, core, radiative zone, and convective zone. And some of these words are familiar to you, I'm sure. When you say radiative, it's energy is transmitted through radiation. And when you say convective, you know that energy is transmitted through convection. Okay, hot matter goes up and the relatively cool matter comes down. Okay, uh, so this is roughly the structure of the sun, and I'm pretty sure is closer to the reality. But who knows, in 5 years time, 10 years time, 20 years time, the scientists will change the model of the sun, right, based on more data, new data, precise data. Right? They might say there are 5 layers, okay, or 4 layers. Who knows? So let's look at the energy core first, right? Um, so this is where the hydrogen fusion takes place. As you already know, hydrogen fusion doesn't take place everywhere. It's only in the core, and because it needs 10 to the 7 degrees of Kelvin, 10 million Kelvin, okay, temperature. So you can get it only at the center. But it's propagating, you know that it's propagating, right? Uh, this core is roughly about a quarter of the solar radius, right? If you measure it from the center to the outer surface, it's roughly about 0.25 mark, 25% the radius. So what surrounds that is the radiative zone. The energy generated in the core in terms of gamma rays, right, they come out of the core and propagate through radiation through the radiative zone. And that is why it is called radiative zone in the first place. Okay. The gamma ray heats up the material there. The total uh, the size of the radiative zone, it extends to about 70% of the solar radius, right? About 70%. Then you get to the outermost layer. This is the internal structure, right? Internal structure. The outermost layer of the internal structure is the convective zone. And it is an opaque zone. You can't see through it. You can't see anything underneath, even though it is gaseous object. Hydrogen is transparent, and sometimes you might wonder, hydrogen is transparent, and why can't we see through the sun? If it's entirely hydrogen, you should be able to see through, right? So, but sun you can't, because this area is opaque, right? You can't see below that. But this is not a very thick area. So this is a relatively small portion, right? Because you see it's standing from 70% onwards, maybe 30%, okay? That's a bit sizable, right? But it doesn't look like 30% from this illustration here. Now, in this area, this layer, the energy propagation takes place through convection. You can see these convective currents like loops, right? So the heated material, right, because of the radiation underneath, right, they get heated and they go up, and it releases the energy to the atmosphere and then come back, goes out, goes up, comes back, like that. Because it's very much like volcano. Maybe you have seen volcanoes on the earth, right? The videos and all on the TV, YouTube. But this is somewhat analogous to the sun, right? The heat is actually coming from the bottom, right? And it heats up things. So hot matter, right? They emerge through the other surrounding matter, and sometimes you will see the sparks coming out of the hot matter, and then relatively cool matter, they go down to fill the gap, right? Fill the space. So it is happening uh, beneath the surface of the sun, right? You can see these convective currents. Here, actually, you can see only two-dimensional structure, right? It's like a loop, one plane, but reality is it's not one plane, it's a three-dimensional structure, right? So you can't have this just two-dimensional loops here. So it happens all over the place. So therefore, you will see it as a three-dimensional loop. You might wonder, what is that? Three-dimensional loop. When you say a loop, it's two-dimensional. Now, there are a series of loops like that to combine together to make a three-dimensional convective unit. Okay, and these units are so many units are there on the earth, millions and millions of three-dimensional structures. Okay, created by the convection. So this is how sun gives out the energy that it produces in the core, 25% radius core, right? So first part is radiation, and then the outermost layer, energy conversion or propagation takes place through convection. So when you come from the inner core to the surface of the sun, right? You pass these three layers, right? Core, radiative zone, convective zone. Now, let's say you are on the surface. Let's say that you're on the surface there. After that, you go out of the surface to atmosphere, right? So the sun's atmosphere also has three parts: photosphere, chromosphere, and corona. Okay, so I think it's again easy to remember, three and three. Three layers internal and three layers external. So you can remember it like that, three and three. Okay. So just above the surface is photosphere, and it's about 400 kilometers thick. And that's the innermost part of the atmosphere. So basically, it is what we see. It is what we see, the photosphere. Okay, as yellowish, and we don't see anything below that because it is again opaque area, right? You can't see through it. After that, you have the chromosphere, big, right? Compared with the photosphere, it's about 2000 kilometers thick above the photosphere. After that, it's very strange thing. There is another part of the sun, we call it corona, but actually there's no upper limit for that. It's like the candle flame, right? Candle flame, you can see the top, but it's changing all the time, right? It's changing all the time. But if you see the inner part of the candle, the wick and the part around that is pretty much stable, right? You can actually measure and say how much. But when it comes to the yellow part, is waving, moving, and the top part is actually fluctuating, and you can't really measure it and say how much it extends. Okay, so corona is very much like that. It extends to millions of kilometers, and it's very dynamic. It changes all the time. So roughly, when it comes to the atmosphere of the sun, you need to remember this information. It has three sections: photosphere, chromosphere, and the corona. Photosphere is the lowest part of the atmosphere, or the part of the atmosphere just above the surface of the sun, and it's only 400 kilometer thick. Okay, it's not that big. And then comes the chromosphere. It's bigger than the photosphere, 2000 kilometers, right? And after that, you have the corona. Now, this is the sun as we see it, right? So what we see there. So you have 6 layers of the sun, let's say 6 layers, 3 inner layers and 3 outer layers, right? Out of these 6, when you get a photograph of the sun, let's say yellow filter, right, H alpha, whatever, this is the photosphere. This is what we see. We don't see anything else. The corona, the chromosphere, they are all transparent, and the photosphere is opaque. Okay, so you can't see through that. So if I pedal back, this photosphere over here, and also the convective zone, right? These are opaque areas, so you can't see through them, right? That is why we can't see, even though it is hydrogen, you can't see the radiative zone, you can't see the core of the sun. So what it would have been had this been transparent or translucent, right? And also the photosphere, it would have been fantastic view, right? You get all the energy from the sun, and you can see through it. You can see through it, right? So I don't know what it would look like, right? Had it been like that. Okay. So because this is what we see, I thought it's good to discuss a little bit more on the photosphere. So the temperature decreases upward. So this is what I really want to tell you. Temperature decreases upward, right? Uh, there's nothing strange here, because everybody knows that, right? You get the heat from bottom and you move up. So you cool down, you give your energy to someone else and you go back, right? This is what the convection is. Um, so therefore, you expect to see the photosphere and also the layer below that, right? To actually give the energy out, and as you proceed upwards, the temperature drops. Okay. Uh, Now, the surface is much more complicated than we would otherwise think, right? Because there are black patches like this on the surface. It's not all even yellow surface everywhere, right? There are a lot of spots like this, and because we see it as spots, we call it black spots, right? Or sunspots. Um, so we'll come back to sunspot, that discussion a little later. And before that, uh, let's talk about this phenomena, limb darkening. Limb darkening. So if you see the sun, right, you will see it's brighter in the center, right? Somewhere here it's much more brighter, but as you go to the periphery, right, it becomes little darker. Okay, we call this limb darkening. Uh, every object, every planet with the atmosphere, right, supposed to have this phenomena, limb darkening. So limb, as shown, limb is the periphery, right? Outer area is the limb. So why is it happening? Why the limb is bit darker than the central part? So if you see from side view, you can see this as the sun, right? And it gives energy out, right, to the observer. And that energy has to go through the atmosphere. Okay, energy has to go through the atmosphere. So when it goes through the atmosphere, right, it gives the energy out. So therefore, the photons that are coming from here with very high energy, when it comes over here, low energy. Okay, it's like you can imagine analogously. It's like wind resistance, right? If you try to throw an object through the air gives a drag and it slows down. Energy is lost, okay, because of the drag. So this is not like that. The energy is given out through convection, collision, like that. So therefore, when it comes over here, it has some amount of energy, less than what it initially had. Now, if you look at how much of energy is dissipated from here to here, right? Uh, then compare it with a spot, an area over here on the limb, right? You can see that all the photons that we see, let's say the observer is over here, right? Uh, that those photons will have to travel a longer distance, maybe 3-4 times as the distance that this photon has to travel. Okay, so longer the distance, more the energy dissipation is, right? So therefore, all the photons that are coming from the limb area, right, they have less amount of energy compared with the photons that are coming from the center of the sun. So therefore, these photons are less energy, so it looks a bit darker. Okay. Now let's look at the what we see on the surface, the photosphere, right? This is the surface we see. Even though it looks like beautiful yellow color uh, body, right? The photosphere. If you see it very closely with high resolution, right? Um, then you start to see actual features of the photosphere, right? So you you saw that right below the photosphere is the convection zone, right? So hot matter comes to the top and gives the energy out and then go back. They come up and they go back. And I explained that this is happening in a three-dimensional space, right? So on the surface, you see it like this. Why? When you there are some areas where the hot air comes to the surface, and these areas are brighter, they're hotter because it's hot matter. And when they give the energy out, right, and go back, they are less energy. Okay, they don't have as much energy as they had earlier. So when they have lower energy, it looks darker. So when they go down this area, right, you see it bit darker, and also here. Now, when you see it from the outside, it will look like this. There are bright areas, there are dark areas. Bright areas, dark areas. And because of this flow of gas, these dark areas are actually connected like a boundary. They are not like randomly distributed, right? In a way, it's kind of random, but there's a connectivity. There's a connectivity of these lines. Okay, very much like in a volcano, right? You get some matter coming out of a surface, and then all the spots like that, they're connected in some way, right? They come out and they go down. So the areas where matter go down, right? So looks a bit darker like this, and the areas where you see more energetic material, hot matter come out, they're a bit brighter. So when you take these photographs, you have to adjust your equipment settings, so that it's always relative to what you see. When you take a photograph, let's say in a dark room or less bright condition, then you open it up, you get more photons into. Okay, you need more light to create the photograph. But if you photograph a very bright object or daylight around noon, a lot of light around, so then you have to adjust your sensitivity, right? Because a lot of photons coming out. Likewise, when you photograph the sun, you are in a very extreme condition, right? You have to adjust your exposure levels to very high levels, or in other words, in camera terms, to very low levels, because it's very bright object. So when you do that, let's say this is 6,000 Kelvin areas, right? These are 6,000 Kelvin areas. These are, let's say, 5,500 areas. Who knows, right? Few hundred degree difference. So when you adjust your equipment sensitivity to that, even this 500 uh, Celsius difference makes those areas darker, look darker. That's how these photos are generated. Okay. But if you do not adjust your imaging equipment like that, you will not see the details. You will see everywhere whitewashed because it's very bright. Even 5,600 is a very bright object. Okay. So this is by technology and by techniques that to differentiate the hot areas and less hot areas on the sun. Okay. You can do it for any other object for that matter, right? To differentiate temperatures. Basically, this is what we are doing. You have seen handheld uh, thermo thermographic techniques equipment. There also you see the body temperature. There you have seen the animals, etc. Okay, in pitch black color because the body temperature is enough to generate those false color images. So technology is there to handle this kind of extreme situations to differentiate 6,000 or 5,800 Celsius with 5,500 Celsius. Okay. So 5,500 becomes like black, dark. So these are beautiful photographs, and you can see very high resolution photographs of the surface of the sun, right? So um, these evidences, visual evidences are extremely important for us to uh, create more accurate models of the sun. So what really is happening there on the sun, right? So these structures actually prove the hypothesis or the theory of this convection, right? Just below the surface of the sun, because the convection, hot matter comes out, and we can figure out these hot areas here, 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 the bright areas. They're all where the hot matter comes to the surface, and the dark areas like here, here. This is the areas where hot matter, less hot matter, right, goes back into the sun, okay, after releasing the energy. Can you see this little movie here, the changes? Can you guys see the variations here in the photo?
Yes, sir.
Yeah. So this was kind of very surprising evidence back in the day. So everybody was really happy to see. Now see, this structure is not static, okay? It is changing very much as you would expect to happen. You can't have anything static there on the surface. The hot matter that is coming from the underneath to the surface, they're not coming same rate, same place, steadily, okay? So it changes all the time. So as you would see here, the structure changes. So this resolution is about 30 kilometers. The smallest thing that you can see here is 30 kilometers big. Okay. All right. So this is not actually far back. This is very recent, 2019. Now I want to tell you about this um, project, NASA project, Solar Dynamics Observatory. Right? I want you to go to Google and find out more details, right? As a homework. But I can show you this remarkable information on the YouTube. So, Solar Dynamics Observatory, I think it was a space telescope launched from the Earth around 2010, and it has been collecting, imaging the sun exclusively for sun observation, okay, for a decade, for a decade. You can see, you can't see the granules here, right? Earlier you saw the surface of the sun, right? Here you can't clearly see it, but you can see the bigger structures now, right? Very bright spots over here, right? Solar flares. And also you can see, as I said, the corona, right? Uh, the photosphere, the chromosphere, and the corona. So it's very difficult to create a margin for that. Is extending and changing all the time. In some areas, you get a bigger corona when there is a very high activity. Now you can see a very bright area here. This is when the sun is actually having a very high activity. The convection that is happening underneath, if you get the nearby area, they're all working together and in sync. Usually it's not happening in sync, right? It's more like random, okay? But if you observe it for a longer period of time, there's a situation that they all get together at some point of time. Then you get a huge activity in that area, localized activity. There you can see the flares, solar flares. It's very much like a flare, right, or a flame. It's not very commonplace for the sun, but sometimes it happens. So when a flare happens, uh, flares are actually coming from very high active areas, and it extends millions of kilometers into the space. This is a long video. This is a long video, right? So I don't have time to play it all, but I want you to leisurely, right, watch it. Not the full length, but you can skip certain areas, right, time to time. Uh, but it would be really interesting to see the different phases of the sun. Even though from here on the earth, we see the sun same way every day. You can see here how dynamic the sun is, right? It looks really intimidating in some phases when it has very high activity. So I think every 1 second in this video is like one day, right? So they have taken one whole day into 1 second. That is kind of compression they have done to speed it up. And you have one whole decade. Now see, you can see the one whole decade of the sun right here on your screen. So this is how the technology brings you the information, the knowledge. Okay. So it's a remarkable thing. Somebody says we can't see the video. But so one said you can see, right? Can you see the video? Can't you see the video?
We can't, sir.
You can or you can?
We can't, sir.
We can't.
Okay. So you should have told me. Wait.
Can't, sir.
Wait. Can you see it now?
Yes, sir.
Now, if I play it,
Yes, sir.
yeah, if I play it, can you see the video? Were you able to see the video?
Yes, sir.
Yes, sir.
Okay, great. So what I was telling you is that what you see here on screen is the sun from 2010 to nearly 2020. Okay, one whole decade. And every 1 second on the video is like one day. Okay. And you can see here few things. The bright areas, these are where you have the very high activity on the surface of the sun. And you can see on the periphery flares coming out of the sun from these very highly active areas. And this is actually the corona, right? Corona is the glare of the sun, right, which goes to millions of kilometers, and there's no particular range or distance for corona, right? So this is very much like the surface over here. You can see that the photosphere and the chromosphere. And on the surface, you can see some dark areas, right? The dark areas are relatively cooler area, like 5,500 Celsius Kelvin, maybe, right? They are not cool. There's nothing cool there. They're also very, very hot, but they are not as hot as these bright areas. Okay, so when I think I explained that in the photography techniques, they use this one. They adjust their exposure levels and other parameters depending on what you want to image, right? If you want to image the sun, they reduce the intensity to manageable level, and then you can differentiate the bright and less bright areas. Now, when I see this, it's really scary, right? Really scary, because I sometimes tend to believe, would it explode next moment? Because it's so violent, right? Sometimes. You can see these nice structures, right? As I said earlier, it's not completely random, right? Even though the convection is kind of happening in a random way, but there is some sort of relationship, right? So when you have a very hot air flow in one point on the surface, right, it has some effect on the nearby areas, right? Nearby areas will have to bring that hot air, right, back to the sun. So then you get these dark areas around bright areas. Okay. So as you saw in the photograph I showed you earlier, but here you can't see that very high resolution information, because you can see the entire sun over here. So this is a the holistic view, right? Uh, the the big picture that you can see over here is not the granules. The granules are too small to see here. This is how these black areas, cool areas are connected, like a region, a big area. Okay. Now this one, look at this phase, right? During a certain moment in that one decade, it looks to me like very peaceful sun, very peaceful sun. There's no big activity anywhere, right? On the part we see, but next moment something is erupting over here. Okay. And over here, so it looks like the bushfire, right? You can see fire going on in one place and the next moment some other place because the wind and all. There's some analogy. Right. So I want to get back to the slide and want to, if you can take down this one, I'll keep it in the
T minus 10, 9.
copy it. So I'm just copying to the chat. If you just look at the chat, you can see the links of the videos, right? At your leisure time later, make sure you view these two videos, right? The second one over here is also a fantastic video.
T minus 10, 9, 8, 7, 6.
And
5,
can you see the video?
4. Go for main engine start. 3, 2, 1,
Yes.
0. And ignition and liftoff of the Atlas V with the Solar Dynamics Observatory.
This is Atlas V rocket with the SDO, Solar Dynamics Observatory, right?
SDO, the Solar Dynamics Observatory, launched on February 11, 2010, and has been watching the sun for the last 10 years, providing key insights into what drives the sun's activity, including the space.
Can you hear the sounds also from the video?
Yes, sir.
Yes, sir.
Okay.
Space weather that our astronauts and spacecraft must travel through.
My goodness. See this one. This is a particular moment they have captured during the one decade. I think in the previous video, we didn't see that. This is a very, very high activity. See, all over the sun, right? So it looks to me, and scientists know about it now, there are certain times the sun gets very angry, right? Highly active. And there are some other times sun is not as active as those peak times, right? So it goes on like a cycle.
During that time, it has
See this resolution. And the world has never seen before the DSO project this information. As you know, in the science world, right? There are theoretical scientists who work on the paper, like Einstein, for example, right? He worked everything on paper, right? Theories, and all. And there are some experimental scientists, right? Experimental scientists. And what they do is they actually try to collect evidence, either to prove or disprove the theories. Okay, so there's always these two groups in the scientific front, and sometimes these the theorists who are actually working on paper, they are called the backseat drivers. Backseat drivers. You see the backseat guys who are teaching the driver to take the turns left, right, and speed up, brake, and everything. So they're like that. They are instructing, giving advice to the driver how to drive and all, right? So in the science world, this kind of joke, right? So they say backseat drivers for the theoretical people who are developing theories, right? So this kind of phenomena, when the experimental scientists, right, when they get this kind of results, the backseat drivers, the theorists, right, it's very challenging for them sometimes to change their theory, change the model, so that the model can explain this phenomena, right? As I said to you, this is how the hypotheses get accepted or rejected over the years. Whatever theory somebody puts in, right, to the scientific world, for it to be accepted or rejected, it is entirely based on the evidence. So this kind of images showing the high energy matter coming out of the surface and releasing that energy to the surface, this is very much in compliance with the convective zone, right, the outermost section of the surface of the sun. So therefore there's no controversy between the theory and the observation here, right?
witnessed incredible solar events and enabled science.
This is another flare coming out of the sun. It happened at the edge, fortunately, so that it was captured. It was the right moment, right place, and it was properly captured. When you see it, there's no difference between a volcano and this one, right? As you see it. But if you look at the material and the temperature, is a big difference. This is basically hydrogen burning, right? Whereas on the Earth is a different matter altogether, and temperatures are also different, right?
Scientists to make many groundbreaking discoveries about the sun. Here are some of the highlights. In 2011, scientists spotted a special kind of ripple on the sun called Kelvin-Helmholtz waves, which look like curling ocean waves. They are also present on the Earth, but aren't the size of the United States. On June 7, 2011, SDO spotted a huge eruption of plasma on
Do you see that? This is a plasma ejection.
SDO spotted a huge eruption of
Have you ever thought this kind of
7th,
phenomena coming
2011,
from
SDO spotted a
sun?
huge eruption of plasma on the sun. This was the first time such a large event had been captured in such fine detail. 2 months later, on August 9th, SDO observed one of the most powerful flares of this solar cycle. Flares are intense bursts of radiation caused by the release of magnetic energy. SDO records in many different wavelengths, including one tuned to some of the hottest parts of the sun, allowing it to see the full extent of these solar explosions. On December 15th, Comet Lovejoy seemed to survive a close pass of the sun, but broke apart.
Now here, this is a very interesting scene that you can see a comet flying very close to the sun.
A few days later.
You see that?
Full extent of these solar explosions, close pass of the sun, but broke apart a few days later.
Yeah, that's a comet.
In 2012, scientists used SDO's wealth of information to create a new and impressionistic way to further understand temperature change on the sun. On June 5th, Venus transited the
This is another remarkable incident, Venus transit. So the black object over here, right in the right upper middle area, is the Venus. I remember capturing a Venus transit in mid-90s, right, at the astronomy center over the lake, on the other side of the lake. Myself and we had a group of people, astronomy loving people there, right? That was when I was an undergrad. We took that. We captured that on a video camera using a telescope and the filters. We captured it. And I think that video we sent to the Rupawahini news the same day they broadcasted it. So it's a very nice scene, and it's a very rare scene as well.
Face of the sun, an event so rare it won't happen again until 2117. In July, SDO's high resolution and rapid...
See this one, beautiful, isn't it? Again, this eruption of matter, right, is circling backwards like a loop. So what you see, the loop over here, I think underneath the surface, you have something similar. You have something similar, right? Because the hot matter comes to the surface and goes down, back again, back to the sun, right? It's happening all the time, but you can't see it because it's opaque. This surface is opaque. Sometimes these loops, right? These loops become so violent, so powerful, they come out of the surface. So that's what really happens. They are there under the surface, right? It's happening all the time like that. But when it becomes very powerful, they break open the surface and come to the atmosphere and goes down.
Rapid imaging cadence captured a beautiful solar loop where hot plasma condensed out of the atmosphere, or corona, and stuck to the strong magnetic fields pushing through the surface. On August 31st, the sun had a huge and beautiful prominence eruption that instantly became iconic. Early in 2013, SDO imagery helped astronomers see the early formation of a coronal mass ejection, or CME, and the reconnection events that result in solar flares. CMEs release giant plumes of material from the sun that speed across the solar system. They can interact with Earth's magnetic environment and are hazardous to...
This is interesting. This is cosmic mass ejection or coronal mass ejection. When you have this very high intense activity and the convective current cycles break open the surface and bring matter into the corona, and there's a lot of dynamics happening in the corona, and you get these particles to like fly like a wind, speeding bullets all over the place, right? They come to the surface of the Earth as well.
Spacecraft and astronauts. The sun was very active in September and October, first forming what almost looked like a canyon and then crackling with flares and CMEs for a week. Comet Ison made its way around the sun on November 28th, Thanksgiving Day, but unlike Lovejoy, it broke apart immediately. The sun
That's-
remained active in
that's another
2014
comet.
with many
Did you see
beautiful
that?
Lovejoy. It broke apart immediately. Comet
see that?
Ison made it.
So there's a comet going, right, having a close flyby around the sun.
Its way around the sun on November 28th, Thanksgiving Day. But unlike Lovejoy, it broke apart immediately. The sun remained active in 2014 with many beautiful prominence eruptions and bright flares. SDO worked in tandem with the new satellite IRIS to help study these flashes. On December 19th, just in time for the holidays, the sun put on its final light show of the year. The sun has a cycle of activity lasting an average of 11 years, called
There you are. You can see on the left, somewhat quiet sun, but on the right, very ferocious sun. So then it goes back to very calm mode. Right? It takes about 11 years.
called the solar cycle. 2015 marked the beginning of the decrease in this cycle with fewer flares and eruptions. On May 10, 2016, SDO saw another transit, this time from Mercury. It looks much smaller because not only is the planet smaller than Venus,
Can you see that? Earlier you saw the Venus transit. The planet Venus is having a flyby, right, going across the sun's surface, right, from left to right. And that was kind of big, right, because Venus is big. And Venus is big and closer to the Earth. And now this time it's Mercury transit. Mercury is very small and also farther away from the Earth than the Venus. So therefore it looks very, very small.
it's also farther away from Earth, where SDO is orbiting at 22,000 miles above the surface in a geosynchronous orbit. The solar cycle had its last gasp of activity in 2017. In July, a large sunspot made its way across the face as the
Oh, this is really, really interesting. Can you see that? This is the sunspot, right? The black area. And maybe somewhere over here we have a bright area, and matter comes out of this area and goes back into the surface through the sunspot. That is why it is a bit black. I'm not sure whether this is a real image or constructed one.
sun rotated. Then in September, a final burst of flare activity, including the strongest flares since 2001, exploded off the sun. Since this activity, the sun has been pretty quiet, sinking into the lowest point of the solar activity cycle.
Yeah, this is the lowest point of the solar activity cycle, 11 years, right?
Scientists were still able to go back through old SDO data and discover a new kind of explosion called forced magnetic reconnection. On November 11, 2019, Mercury transited across the sun again, this time with
Can you see the Mercury over here? Because Mercury is close to the sun, it goes around and around very quickly compared with the other planets. So you can see more transits of Mercury than any other planet, right?
a much more sedate backdrop. SDO scientists are aiming to continue watching the sun for at least another 3 years, and the spacecraft could even last another decade. During this time, it should witness the rise of the next solar cycle and an increase in solar activity. Without a doubt, SDO's last 10 years changed how we looked at and thought about our nearest star. Who knows what the next 10 might bring?
Yeah, so fantastic. This set of observations, whole 10 years from 2010, and possibly it will go for another decade, closer to a decade. And this has already changed the way we look at the sun, right? Pretty obvious. Amazing pictures and videos and proving some of the theories and giving opportunity for theorists to improve their models, to make it more closer to the reality, right? Because without this kind of videos and data and evidence, even theorists cannot build their models entirely on paper. because they should be guided by something, right? And that something should be definitely the evidence again. Okay, so this is going like back and forth. You generate your model and you wait for the observation, the evidence, and when you get the evidence, you are guided by the evidence again. Okay, so it's a very fantastic cycle of theory and evidence. Okay, so I think you have both of these videos in the chat room. Please copy it and watch it leisurely. Watch it leisurely. Okay. Right. All right. Now it's time for us to get a little break. Any questions about sun so far? Before we break for 10 minutes, any questions, please, up to now? Okay, fantastic. Then I'll see you in 10 minutes.
T minus 10.
Okay, welcome back. So let's continue with where we stopped before the break. Now it's into the chromosphere and corona, right? Our discussion, we have come out of the photosphere into the next layer of the atmosphere of the sun, that is the chromosphere, and next is the corona. As you can see here, the graphical illustration, right? So in the chromosphere, you can see it over here, right? Very close to the dark area of the sun. This is because of the mask. So if you want to see any features of the corona, right, you have to completely take the brighter area of the sun up to photosphere out. Okay, so these are standard photography techniques, imaging techniques when it comes to the sun. Using this half a degree diameter mask, you can completely hide the sun. Then what you see is the bright halo of the sun. All right. So basically, corona and anything outward. So there, if you watch closely, you can see the spicules, right? Like that. It's like a burning fire, right? As you see it, burning fire. And if you adjust your imaging techniques, exposure levels and all, you can see far or less, right? Depending on how you adjust your settings. In this image, you can see again, the sun is completely hidden by the mask and you can see the corona, but we have given some higher exposure to the corona side so that you can see a larger area, right? Then you would normally see, can see it here. This is the complete ejection of matter from the surface of the sun. And you can see the structure, where they're going, which directions they are actually having more compared with the other areas. But the thing is, you can't see any details nearby. So therefore, it depends on what you want to see. If you want to see the chromosphere around the sun, you need to get this kind of image captured. And for that, you have to set your parameters, right? So that you don't see much of the corona going out of the surface of the sun, but the area which is very close to the surface. Okay. The corona is the area or the section of the atmosphere of the sun where you get matter out or release to the outer space from the sun. Now, based on the models scientists have developed, right, based on the evidence that they have gathered, this is a very simplistic illustration of what's going on the photosphere and the chromosphere of the sun. So on the image, on the illustration on the left, you can see the interior. This is the convective zone of the inner surface, the outermost part of the internal structure, right? And then you have the photosphere, somewhere over here, a bright yellow color. This is what we see. And then next to that is the chromosphere. Even though we said it's about 400 or 2000 kilometers, right? Whereas the photosphere is like 400 kilometers, right? It's about 4000. Again, there's nothing static there. Things are very dynamic and changing. And sometimes you get the spicules like that, like the waves on the surface of the sea. Sometimes they collide and you get a little bit of water out of the surface suddenly, something like that. And then there's something strange here. Maybe scientists were not expected that kind of thing. This white area, and then the corona. So corona, we understand this is the halo extending millions of kilometers. That is the matter plasma basically coming out of the sun. Okay. But in between the corona and the chromosphere, there is a small area, white color. So what is that? I want you to pay attention to that. Okay. Because that is the highlight here. That is the strange thing here. Actually, these areas have been actually measured for the temperature. So interior, photosphere, chromosphere, and extending outward into the corona. And this is what they have got, right? In the other diagram, it looks like turning this diagram by 90 degrees clockwise. Okay. So there you see the height above the photosphere as your x-axis, where this is the height above the photosphere as the vertical. Now it is horizontal. Okay, you have toppled it by 90 degrees. And now the y-axis is temperature. Y-axis is temperature. So you can see over here, right? If you take the chromosphere, right? Temperature is just hanging over this area, like this is 10 to the 4, 10,000 Kelvin, right? So maybe this is 5,000, 6,000. That is the photosphere temperature. Chromosphere may be a bit higher than that. But if you look at the corona, the temperatures are very high. And in between, you don't have much of a space, right? Suddenly, you get very high temperature. Very high temperature. Of course, we know the matter density in the corona is extremely low compared with the chromosphere density, right? Because of the volume expansion and all. So you expect to see temperature drop. You never expect to see a temperature rise there. Nobody would have anticipated this, right? Except for people like Einstein, who was always thought against the norm, right? Everybody almost would have thought the temperature to drop gradually, right? When you come out of the surface. If you look at the internal core, right, where you have the nuclear fusion, is very hot. And then the radiative is on, convection is on, photosphere. So as you come out of the energy source, you're supposed to cool down a little bit, right? You can play around with all the other laws of physics like inverse square or whatever. So, but all of these theories say cooling, cooling, cooling. But now, after the chromosphere into the corona, you get a huge temperature difference increase. But if you, well, now you can't challenge the observation, right? This is an observation-based claim, right? It's not a wise idea to go against it, right? It's proven the temperature in the corona is higher than in the chromosphere. So now somebody has to explain it. So you have to approach this logically. For any volume of matter to be of higher temperature or heat it up, you need to give an energy, right? Energy source. There should be some energy source here. So now let's look at what is that energy, right? So they are got to be, you got to have an energy source here in the chromosphere to heat it up, to heat it up. Say, think about microwave ovens. Now that's an energy source. You give that energy to the food, to water, and heat it up. Something like that. There should be some sort of microwave effect or some energy source heating the matter in the corona, right? And that turned out to be the magnetic fields. It's kind of magnetic heating that is going on in the corona. Okay, so you can use the magnetic field as an energy source to transfer energy. So that's why we are now into magnetism. So let's talk about the magnetic structure of the sun. Okay, so sun has a north pole, south pole, because now to make the long story short, when you have charged particles and they are flowing, there's a motion, right? You are generating a magnetic field. Simple. In the sun, you have charged particles. You can say, okay, you have n number of protons and n number of electrons. So they are neutral, fine. But as long as they are together, it is neutral. But when you take them apart, electrons are somewhere, protons are somewhere else, right? They are not attached and neutralized individually. So therefore, you can see some imbalance. More protons in one area, more electrons in some other area. So that is the separation, and this is where you give rise to magnetic fields. As long as all these particles are homogeneously distributed, probably they are attached to each other, proton, neutron, proton, electron as a hydrogen, right? Then there's no magnetic field, even though they are moving. But if you take the proton and electron separately and let them to move, they are causing magnetic fields, very complicated magnetic fields, right? So this is what is happening in the sun. So the corona must be heated by a source other than the conduction or radiative diffusion. Of course, yes. Radiation or convection, right, cannot be the source here, source of energy. So let's look at sunspots then. Sunspots are actually low temperature regions in the photosphere, and they appear dark because it's cooler relatively. So mind you, anybody who has observed sunspots through a telescope with a filter? No one? I can tell you a little story. When I was an undergrad, many years ago, right? I was like you. I was attending lectures, and I make it a habit for some 3 months. When I got the lunch break, I used to have a 10-speed bicycle, racing bicycle, and I got on the bike and I rode it to the astronomy center just across the river on the other side. And I went directly up to the observatory. You can see if you go to the boatyard of the university, you see the other side of the river, you see the white building rising through the rubber trees, and that is our observatory there back then. And I had a little telescope equatorially mounted, with the filters and everything. I was just watching the sun and sketching it, right? Sketching it and taking measurements of the sunspots, where the sunspots are. I was doing this for how many? Nearly about 2 months. I really wanted to do only for 1 month, 26 days or so. That's the sunspot, rotation of the sun. I was doing this during lunchtime, and then around 12:40, I was done, and then I got on the bike again and rode it back to the university. Had quick lunch, and by about 1:10, I'm back in the lecture room. Okay, so there was a time like that. I actually encourage you to do something like that. Not exactly sunspot observation, but anything else for that matter, right? Don't waste your time. Those are precious experiences if you engage. Right? Do not just be a bookworm, just reading books, whatever, spending a lot of time on the videos, etc., etc. Right? Make some creative time for you, right? And you will remember it forever. And the experience you get out of those experiences, time you spend creatively, that will never fade out of your memories. So every time I teach about this sun and sunspot, that comes to my mind, right? The time I spend there during lunchtime, riding the bicycle to the astronomy center observatory and doing the manual sketching and all that, and taking measurements and calculate rotation period of the sun. Okay, the rotation period of the sun is not a unique thing because the sun is not a solid body, it's a gaseous body. So it depends on the where you look at, where you want to measure the rotation period of. If the sunspot happens to be near the equator, you get a one rotation period. But if it happens to be somewhere in between the equator and the pole, as you see it, right, you get a different uh, period of rotation. So whatever it is, it's really interesting that you find it yourself, your own calculations, your own measurements, and you get some number, right? How far off that from the accurate value, it doesn't really important. It's not really important here. But what's important is that you find it yourself. So when I see this one, it looks to me like what I did back then, right? I saw sunspots coming, appearing on this edge, and then following days, they're moving like that, and also they're changing. Sometimes you can see, right? It's not the same structure, it's changing, right? It's changing. So, so because I have had this experience myself, so it's very close to me, resonating, right, of what I was doing. So pretty fantastic set of images, right? From November 9th to November 17th, which year I don't know, but it doesn't matter. What's important is the time difference, right? So if you collect all this information, how many sunspots you see, right, at a given moment of time, and then track it over the weeks, months, years, this is what you get. From 1750, I don't know how accurate these observations were back then, right? And like leading up to about 2000, you can see a clear pattern, right? You can see a pattern. Of course, it's about 11-year cycle. Every 11 years, you get to the peak. A lot of sunspots. Now, the sunspots are actually associated with what? With the activity of the sun. Activity of the sun cannot be actually visibly seen, right? There are other ways you can feel about it. But what you can see is the sunspots. So there's a direct relationship between sunspots, the numbers, the intensity, how big they are, and so on, with the activity of the sun. Now, the activity of the sun is basically the magnetic field. If you want me to pinpoint as one single thing on the sun which is responsible for the activity, I would say magnetic field. So the magnetic field structure is changing, and it's becoming intense. And sometimes after about many 5-6 years, it goes down to neutral level or low level, and then pick it up after about another 11 years. So this magnetic field intensity is another facet of the intensity of the sun. So observation part is the sunspots, how many and their groups, their size, etc. Okay. So as you see here, the average number of sunspots increases and decreases in a regular cycle of 11 years, right? With reverse magnetic polarities from 11-year cycle to the next. So every 11 years, you get the magnetic pole reversed, because the whole thing starts with the magnetic field structure, right? It gives rise to all the other activities on the surface of the sun, including the sunspots. More sunspots are generated because the magnetic field, and when the magnetic field is very intense, you get more sunspots. Okay. So for your information, the last solar maximum was in 2011. So there you can see around 2000, slightly, yeah, after 2000, it looks like the maximum, solar maximum. And then when it comes to our time, after 2000, the maximum has been reported in 2011. Okay. So if you plus another 11, maybe 2022. Okay. This year. Wow. But we don't have the peak this year, right? Is kind of delayed this year. The next one is expected to happen in between 2024, 26, maybe 25. Okay, so you don't have very regular 11-year period, just like the rotation period of the sun, the earth, the moon, etc. This is a fluid body, right? So things are changing. This 11-year period is roughly 11 years. Sometimes can be 10, can be 14, right? Now, I would like to throw at you some really strange, unusual things that you cannot find in normal presentations, right? One of these things is Zeeman effect, right? So I'm sorry if I'm dragging you too much into technical things, but I'm not going to explain you any technical things, but make it like a story, right? And I think you can follow it in that flavor without much difficulty. Now, this discussion bit about this solar activity and the magnetic fields and the sunspots, right? Somebody has to clear this, right, in various ways, right? So this is another attempt, interesting attempt to find some harmony, right, in this problem, because this is very irritating problem for some scientists who really want to see things very clearly. But unfortunately, in this discussion, sun's magnetic fields, the solar sunspots, etc., there was a time it was not very clear, right? Very frustrating why it is happening that way. So now the Zeeman effect says, well, it's a bit complicated. Let me show this one. Yeah, I think this is the best way to explain it. So what you see here is the energy orbits, energy bands of an atom, right? You can see 1s orbit and 2p orbit of electrons, right? To have certain amount of energy, because quantum of energy. Electrons are around an atom, right? A nucleus. They can have either 1s energy level, 2p energy level, whatever it is. So usually what you see is when you get energy, these electrons jump from 1s to 2p temporarily, but they're not stable there, right? You can't have a vacancy here. You jump up because you got some energy, but immediately you have to come back. And when you do that, you release that energy. Okay. So this energy that you release when you go back to where you came from, this is a very specific wavelength, very specific wavelength. Let's say this is an electron which is jumping from 1s to 2p and coming back. It's an electron of a iron atom, right? So then the energy from 1s to 2p for iron is a very specific wavelength. So if you see in space somewhere in a nebula or a star or somewhere, you are receiving that energy, that wavelength, right? You can say, oh, I think there is some iron there, right? There's some iron there. Again, you can see the dual of that is the absorption of energy, right? If you have a wide range of energy, right, out there, and if you have iron there, iron will absorb this energy, exactly this amount of energy, it will absorb. Okay, so then all of a sudden, out of this continuum of energy from very low wavelengths to very high wavelengths, that particular energy level is missing. It looks like a black line on the spectrum. That line is missing. You have all the energy levels, all the energy is from left to right, but at that particular wavelength, that energy is missing. Okay, so if you capture the spectrum of the sun, let's say, right, when there is no magnetic field and there is iron there, or aluminium or carbon or whatever, right, and there is a specific wavelength that is being absorbed by that particular molecule or atom, right, and you see that wavelength is missing in your spectrum, and you know now because of that there is some iron there, there's some carbon there, there's some aluminum there. That is how you identify the chemical composition of a sun, right, of a star, of a nebula, or whatever, looking at the absorption spectrum. Clear? Now, if you have a strong magnetic field in this area, now you have the energy source abundant, all the wavelengths are there, right? Whatever wavelength you want to absorb, all the wavelengths are there, right? And you have this particular element, let's say iron, right? And iron absorbs this particular wavelength. So you expect to see this black line. And in addition to all of these things, if you have a strong magnetic field, the Zeeman effect says this magnetic field, very strong magnetic field, will split the 2p energy level into 3 areas. Now it is not just one energy level, but 3 energy levels. 2p1, 2p2, and 2p3. This happens because of the strong magnetic field in that area. Okay, so then what you expect to see in your absorption spectrum is something like this. In place of just one single absorption line, you now see 3 lines parallel to each other, very closely apart, very closely apart. So how wider or narrow they are placed apart depends on the strength of the magnetic field. Stronger the magnetic field, higher would be the gap between the absorption lines. So this is a physical theory law, we call it Zeeman effect. But now you see, if you look at the absorption spectrum, of the sun, not everywhere, but in the area of a sunspot. This is a sunspot. Now you get the spectrum of that area, right? Maybe this area, the small area. This is a sunspot, and you see the Zeeman effect there. This is a line, right, above the sunspot. This is below the sunspot, right at the sunspot, right? The line is split into three. So this is a clear evidence that, okay, let me ask you this question. When you see this photograph, this spectrum, right? This is the photograph of the sun where you took this spectrum off, and this is the spectrum. Can anybody explain me what we see here and why it is happening that way? Can anybody explain on my behalf, please? Any volunteers? Everything is on the slide. You just need to explain to make it a little entertaining. Can somebody explain what we see here? Dinuan, are you there? Dinuan? Umindu, are you there? Kisara, are you there? Vimalasena, are you there? Is there anybody out there?
Yes, sir. Yes, sir.
Sorry about that. I couldn't hear. There's a little problem with the speaker. Okay. Yeah. So can somebody explain? Sorry about that. It's a problem with my speaker. Now I can hear you. Can somebody explain what we see here? Cruz? Cruz, are you there?
Yes, sir.
Yeah. Cruz, can you explain what we see here? Anybody else, please? Please unmute your microphone and explain what we see here.
It's a spectrum, sir, confused by magnetic field.
Now you can see this one line here, right? This is the absorption line, right? And here also you can see the line, same line, but here it is split into three. Why is it?
I think the effect of magnetic field in the
Yes,
sun
right.
surrounding.
Yeah, so there should be a strong magnetic field here. Otherwise, this line would not have split into three, right?
Yes, sir.
Now, what is this location? If you look at the left-hand side, it is this area. it is right in the middle of a sunspot. So now we know sunspots are places of strong magnetic field. Okay, so that is the conclusion here. If you have a magnet, it has north and south. So north and south are very strong because all the field lines concentrate at the poles, right? North pole or south pole. There's strong magnetic fields. This way or that way, it doesn't matter. They are strong. But everywhere else, even though there is a magnetic field, they are not as strong as in the poles. Did you get that point? So magnetic field is everywhere, but it doesn't make this line split. But splitting happens only here because these are magnetic poles, as you see. So there are north, south, north, south, north, south, like that, magnetic poles everywhere on the surface of the sun. This is different from the Earth's magnetic field. Earth also, there is north, south, okay? Two poles, north pole and south pole. Sun is different. Sun has so many of these things, very small, small, small magnetic dipoles, north, south, north, south, north, south, like that. So many. So many. But in addition to that, there is a big two poles, north and south. That is a separate thing. Okay, there's a big, the sun is like a big dynamo, right? So it has its own poles, north and south. But here you have small magnets all over the sun, especially where you see sunspots. So now did you get that point? Now I think if you have followed this properly, you can create a complete structure of the sun, right? In addition to what you see, now you can see sun in a different perspective, the magnetic perspective, right? Sun as a magnet, not like Earth, but there's a big magnet north-south, but in addition to that, there's small magnets all over the surface of the sun. So for that, sun is a very, very different object, okay? Great. Now, if you multiply 11 by a factor of 2, you get 22, right? So there's another 22-year solar magnetic cycle also, because when you have the north-south poles swapping each other in 11 years, and after another 11 years, they swap again, then you get the north pole back onto the same position. So that takes 2 cycles, okay? 2 cycles of solar activity. So one solar activity cycle, which is roughly 11 years, it goes from maximum sunspots to the next maximum sunspot scenario. But during that time, the poles of the sun changes. North becomes south, south becomes north. The next cycle, this will be corrected back. So therefore, 2 11-year cycles are needed for the magnetic field structure of the sun to get back to its original orientation. Okay. Now, in this illustration, you can see the rotation of the sun, right? Rotation of the sun in false colors, right? You can see right in the core of the sun, right? Core of the sun, it is rotating like 27 days, right? Like 27 days. But when it comes to the surface, this equatorial area, this area, it's like 26 days, 26 days. And on the surface, this area, top surface, near the equator, similar to the equator, right, of the Earth, 25 days, fastest. So the matter on this area around the sun is fastest in motion. Next to that, little beneath the surface, 26 days. Now imagine a situation like that. The top layer is moving fast, and the layer next to that is moving little slower, and they are all carrying charged particles. You need to have a supercomputer to simulate and figure out the effective magnetic field structure. So what sort of magnetic field is going to be generated by these moving charged particles? And if you go to the polar areas here and here, is even slower, 30-35 days. So there's hardly any motion there compared to this one, right? So if you compare the charge particle concentration and their motion, their speed and direction, right, you can make a computer model of the magnetic field structure of the sun. Very simple illustration of that is here, right? If you just take a moment on the far left corner, right, you can see the magnetic field line, right? North pole and south, it goes like that, just one field line. And after one rotation of the sun, the equatorial part, this area is which is moving faster than the other areas, now they are leading ahead of the others. So therefore this magnetic field line gets distorted like that a little bit. And if you continue this for another rotation, 2 rotations, this distortion will be even more, and eventually it becomes like that. So it's a very complicated magnetic field line structure, and all of a sudden you get the material coming out of the surface and going down. At a sunspot, you generate a north-south pole over here. So this is where you get these sunspots. So this is a very simple illustration, but yet logical, I think. Now you can explain, you can tell this story to your younger brother or sister, right? There are something called sunspots. They are generated because the magnetic field and the field lines are very complicated because of the differential motion of the matter on the surface of the sun. Long story, right? But it's very logical, and I think you can understand. Okay. Now, the last part of the lecture is coronal mass ejection, CME. Corona is the part of the atmosphere of the sun where matter gets ejected, right, completely from the sun. These are plasma, high energy particles flowing through the space. In order for this high energy plasma to eject from the earth, there should be a violent activity, right? And that's what you see over here, the corona here and there, right? When those CME happens, right, it's like explosion, and you get matter out into the space. And some of these matter will come towards us, towards the earth. Okay. So over here you can see that CME, coronal mass ejection, is a very violent ejection of matter. Sometimes smaller ones actually they emerge and go back to the surface, but the very powerful ones, they completely eject matter altogether, right, from the surface of the sun. And they fly like a wave front, right, just like a wave front. And when they come over here, they are also charged particles. They don't hit directly on the earth because of the earth's magnetic field. We have a magnetic field here. When you have a magnetic field and there's a charged particle coming into the magnetic field, the magnetic field diverts it, right? Diverts it. So this diversion happens here. And there's a wave front here, shock wave front here. And at that point, the matter coming from the sun, the charged particles, they move around the earth. without being able to hit on the earth directly. Okay, but as a result of that, the earth's magnetic field gets distorted, right? So the magnetic field gets the heat and it gets distorted while protecting us here on the earth. Okay, there's a damage to the magnetic field of the earth, and it's a temporary damage, hopefully, right? And the matter goes away, and then earth can restore its magnetic field. But if we get a very, very strong coronal mass ejection activity, so that there's a lot of matter coming towards us, very high energy matter, this distortion of the magnetic field of the earth could be very, very big. So it can be so big that this matter can actually reach the surface of the earth on one side. Okay, so if that happens, it can have devastating effects on anything in the air, the airplanes, satellites, everything. Okay, so therefore now this is becoming part of the weather, just like the sunshine, the rain, thunder, like that. CME is another part of the weather, and still we don't call it terrestrial weather. Terrestrial means bound to earth. We call it space weather. So like we check the weather on our app mobile before we set off from the house, whether it's going to rain today, whether I need to bring an umbrella, etc. Right? Those who are flying, those who are in the telecommunication industry, satellites, etc., they keep track on space weather, whether there's a coronal mass ejection, okay, and what is the weather like in space. So that's a different job, different profession altogether. That's it. Any questions, please? All right. So if there are no questions, let me wind up for today.